Hello and welcome to Engineering Physics 3004, Fluid Mechanics and Heat Transfer. Fluid mechanics and heat transfer are pretty connected. Check out this Engineer Guy video for an example of how heat transfer is affecting how fluid flows, and if you've ever stepped into the breeze of a fan or maybe outside in the winter, you've noticed how fluid flow is affecting heat transfer. The first part of the course, we're going to talk about fluids. A fluid is just a substance that deforms continuously when acted upon by an external shearing stress of any magnitude. So as opposed to a solid, which will change shape, but then as it changes shape, it builds up more and more force and eventually will resist the force that you're applying to it or maybe break. A fluid, it's not so much that it will only move a certain amount in response to a shearing force. It will move at a certain rate in response to a shearing force. So if you give it enough time, a fluid will fill any shape. It will keep deforming in the face of external shearing forces. We're going to break up our study of fluids into statics, which is fluids at rest and the forces on them, and fluid dynamics, which are forces that show up because fluids are in motion. And let's look at some terms. Density is rho, which is mass per unit volume. Specific weight, given the symbol gamma, is the weight per unit volume. So it's the density multiplied by little g. Specific gravity is the ratio of the density of a given fluid to the density of water. So specific density, density has the units of kilograms per meter cubed. Specific weight would have the units of newtons per meter cubed, and specific gravity is unitless because it's comparing everything to water. Viscosity is a measure of how much the fluid is pulling other fluid that it slides past. So it's a quantity that measures how easily the fluid flows, that is, how it responds to shearing stresses. If it responds a lot to a shearing stress, it is inviscid. If it doesn't respond very much, then it is very viscous. Pressure is the force per unit area, usually exerted by a substance's atoms onto a surface. So when atoms crash into a wall, they bounce off and experience a change in momentum from doing that. If you average that over time, then you come up with force units. And if you average it over an area of wall involved, then you can get what is defined as the pressure. Pressure has a lot of different units. Atmospheric pressure is about 1 atmosphere. That's a pretty convenient unit, but it's not SI. SI, it would be 101.325 kilopascals, which is close to 1 bar or 1 barometric pressure, similar to an atmosphere. 760 torr similar to millimeters of mercury, or 14.7 pound-foot per square inch if you're a ridiculous person. Anyway, there's a lot of different used units for pressure, and you maybe unfortunately do need to be able to deal with any of these, because if you get an old piece of equipment or even modern pieces of equipment, you'll still find that it measures in torr. One of the vacuum pumps that I have in the lab is has everything gauged in hectopascals. So got to be aware of how to use all of the different pieces of pressure measurement. Now, if you're measuring pressure relative to zero pressure, that's called absolute pressure. Most of the time, if you just take a pressure gauge and you put it on maybe a tank, then you're probably going to be measuring gauge pressure. And that's because it's really looking at the difference in the pressure between the pressure in the tank and the pressure on the other side of the gauge, which is 1 atmosphere. So as long as you are sitting in 1 atmosphere of pressure while you're reading the tank, and I hope you are for your health, then the pressure gauge is actually measuring the difference between the pressure inside and 1 atmosphere. So you have to keep that in mind. And it's almost never obvious just from the number whether the pressure was gauge pressure or absolute pressure. So you have to understand from the context. There's also vacuum pressure, which is the opposite of this. It's negative gauge pressure. So you could say that we've got maybe 50 kilopascals of vacuum pressure. Maybe that's a bad number because it's close to half of this anyway. 20 kilopascals of vacuum pressure would mean that we are 20 kilopascals below 1 atmosphere. For really high vacuum, this becomes inconvenient. So you're talking about 101.2 kilopascals of vacuum pressure. That's not a very good measurement. So most of the time for high vacuum systems, they actually measure absolute pressure. All right, now we're going to get to the actual content of the text, which is where we're going to spend most of the rest of the course after this intro to get you up to speed there. And the text for the course is Fundamentals of Thermal Fluid Sciences, 5th edition, which is the course text written by Cengel, Turner, and Cimbala, published by McGraw Hill. All right. So the first part is Introduction and Properties of Fluids. This is chapter 10. And although it's chapter 10 and called Introduction to Fluids, that's because the first half of the book has some other great stuff that you probably did in Engineering Physics 2 NE3. We're going to pick up from where that course left off. 10.1 is the no-slip condition. This is talking about a pretty important thing that we're going to deal with for the rest of the course, and it's the idea that because of viscosity, velocity of a fluid can't change instantaneously. So velocity of the fluid is going to be continuous from one spot to the next in the fluid, and that includes at boundary walls. So at this wall right here, we've got the fluid that's right next to the wall has to be moving with the wall's velocity, which means it has zero velocity relative to the wall. Now, the boundary layer is the region of flow close to the wall where the influence of the wall is felt. So we've got some increase in the velocity as we move out from the wall, and that's the reason it's changing at all. The reason it's not just the free stream velocity over there is because of the wall, because we're in this boundary layer. Flow separation refers to this idea that you might have seen, or this phenomenon that happens, where in this picture, fluid is moving from the left to the right here, and it's going around some cylinder. That's this kind of black circle looking thing. And you can see a boundary layer where the fluid is not the free stream up here, but it's influenced a lot by the wall. And then the boundary layer kind of separates from the surface. Now, even though some crazy stuff happens in this wake region, the no-slip condition is still satisfied. So the velocity is nowhere in here changing discontinuously. No temperature jump condition is the same kind of idea, except for temperature. Two objects in contact have the same temperature at the point of contact. More terms in 10.2, classification of fluid flows, viscous versus inviscid regions of flow. A viscous flow is one where the viscosity, or the viscous effect, is important. So flows in which the frictional effect is significant, whereas inviscid flow means the viscous forces are negligibly small compared to inertial or pressure forces. They're always there, they're just not necessarily important compared to what else is going on. Internal versus external flow. Internal flow is flow through something, while external flow is flow around something. We're going to spend one chapter on external flow, that's chapter 15 in the book, and internal flow is going to be in chapter 14. So we're going to spend one chapter on that too, but we're going to spend more time on it because it's a little bit more complicated and a little more important for some of the stuff we're going to be using this course for afterwards. Compressible and incompressible flow. Compressible flow means that density changes are significant in response to pressure variations due to the flow itself, while an incompressible flow, it doesn't. You probably think of gases as being pretty compressible, whereas liquids are not compressible. But with compressible or incompressible flow, we're talking about something a little bit different. A gas flow can actually be incompressible as long as the Mach number is low. Mach number is the speed of the flow divided by the speed of sound. So if the Mach number is less than about 0.3, so we're moving at less than around a third of the speed of sound, or if we're talking about air, less than about 100 meters a second, then the density changes of a gas in that flow are typically less than 5% because of the flow itself, so we can take it as incompressible for most applications. Here's a Schlieren image of a spherical shock wave produced by bursting a balloon. A shock wave is happening when the fluid velocity is at or faster than the speed of sound. You've probably seen this in maybe a picture when an F-18 is breaking the sound barrier. There's this shock wave that shows up right around it. Schlieren movies, by the way, are really a combination of light physics and fluid mechanics. So go and have a look at this second video if you want to know how they work and how to make one, or go look at the first and third videos if you just want to see some cool stuff showing with Schlieren movies. Next is laminar versus turbulent flow. This is going to be very important later on in the course. Laminar is smooth flow. This happens at low Reynolds number. This is another thing that's going to be very important. Reynolds number is the ratio of the length scale times velocity scale of the fluid divided by its what's called kinematic viscosity, which is the dynamic viscosity divided by density. We're going to introduce all of this stuff in due time. Reynolds number is basically a ratio of the importance of inertial forces to viscous forces. So for things that are really big or moving really fast, inertia dominates viscosity, but for smaller, slower things, viscosity is more important. So at low Reynolds number, the flow is laminar, which is kind of smooth, and you could imagine that the flow is kind of pulling the fluid around it to keep everything all kind of in order and behaving itself, whereas in turbulent flow, chaotic flow, high Reynolds number, now we've got the flow is moving really quickly, but because there's still viscosity perhaps, the flow can't keep up, and it's maybe if you think of laminar as like a smooth, solid, behaving itself kind of flow, then in turbulent flow, it's like when you push an object too hard, or a brittle object too hard, and it's breaking. So things are linear relationships and nice things that are happening in laminar flow are all over the place. And even though turbulent is quite crazy compared to laminar, it still behaves itself on average to some extent, so we can still do some cool physics with it. Natural versus forced flow refers to whether the flow is from something natural like gravity or buoyancy rather than forced by a pump. So here's another Schlieren image of natural convection. You, right now, are surrounded by a thermal plume of rising warm air. That's pretty neat. Now, steady versus unsteady flow. Steady means that it doesn't change with time. Remember that uniform means it doesn't change with location. Unsteady means that it does change with time, divided into periodic and transient. So unsteady flow could be, if it's repeating itself, changes in a cyclical fashion, repeats some kind of pattern, then it would be periodic, unsteady. And if it's transient, then it means that there's temporary effects in developing flow. So this is something that is changing with time in a non-periodic way. It doesn't just keep looping back on itself. Even unsteady flow can often have well-defined behavior if we average over a sufficient time interval. And there can also be unsteady flow, which isn't periodic or transient, by the way. Here's an example of a waterfall. Hamilton, where McMaster is the waterfall capital of the world. So go and check out some of those while you're here if you haven't had a chance to do that yet. And here is a version of the same picture, but with a longer camera exposure time. And you see it looks kind of a lot more predictable. What's true about this is that you could take this picture and then you could take another version of the picture and another version, and with the right exposure time, all of these pictures would look the same, whereas these ones would look different with a short exposure time. So it has short-term changes in time, but long-term smoothness. I'll leave that as an assignment for you to go out and take some pictures of waterfalls. Next, we've got 1, 2, and 3D flow. So this refers to where the flow is changing. So if the flow itself, the fluid velocity, let's say, is a function of x, y, and z, so it's not holding still in any other dimensions, or maybe around a circle, if we're in cylindrical here, for instance, r, z, and theta. If it changes with respect to all three of those, then it's 3D flow. Most of the time we're going to deal with 2D flow that becomes 1D after the flow is considered fully developed. So here we go. At the entrance of a pipe, for instance, the flow is symmetric with respect to theta, or it doesn't change with respect to theta. If you move further into the pipe, though, the velocity can change. You can see here the velocity is different than it was at the same r at a different z, and then different still there, different still, different still. But once it's fully developed, it doesn't change with z anymore. It just changes with r. So it's not the same in the center as it is near the walls. So out here, maybe we have 3D flow. And then in the developing area, we've got 2D flow. And this is one-dimensional flow. All right, 10.3, vapor pressure and cavitation. Saturation pressure is the temperature when a substance changes phase. So for instance, liquid to gas. Saturation pressure is another way of looking at the same thing. It's the pressure at which the substance changes phase for a given temperature. So saturation temperature will depend on the pressure. Saturation pressure depends on the temperature. So an example is water's saturation temperature at 1 atmosphere is 100 degrees C. You've also heard this called boiling point. So specifically, the boiling point of a fluid is the same as the saturation temperature of that fluid at 1 atmosphere. But saturation temperature is broader than that. It can refer to whatever. It's still called saturation temperature if we're talking about pressures other than 1 atmosphere. But boiling point is only at 1 atmosphere. Now, saturation pressure is the other way of looking at it. So you'd say the saturation pressure of water at 100 degrees is 1 atmosphere. And this means the same thing. This means that if you were to lower the pressure below 1 atmosphere for water at 100 degrees, the water would evaporate. Water is going to saturate the space around it to 1 atmosphere, to its saturation pressure at 100 degrees. Partial pressure is whenever you've got a gas in a mixture with other gases, then the partial pressure is the pressure that that specific gas would have if all of the other gases disappeared and that gas could fill up the volume by itself. So if the partial pressure of a gas let's say the pressure in the room is 100 kilopascals, and you have one gas that has a partial pressure of 20 kilopascals, that tells you that if there were no other gases in the room, that one gas would have a pressure of 20 kilopascals. So it means that on a molecular basis, it's about 20% of the molecules in the room, all the other mass stuff that factors into pressure equal. Vapor pressure. Pressure exerted by its vapor in phase equilibrium with its liquid, equal to the saturation pressure for a pure substance. So if you lower the pressure below an object's vapor pressure, it will completely evaporate. Even at pressures above the vapor pressure, though, it'll evaporate until the partial pressure of its vapor is equal to its vapor pressure. So here's water molecules in the liquid phase, and then up here there's water molecules in the vapor phase. And you see some of them are up there. They're kind of floating around. The water's not completely boiling yet because we are not at a temperature above the saturation temperature, or maybe not at a pressure below the saturation pressure. But still, the water will evaporate until the partial pressure of the water is whatever the water's saturation pressure is at that temperature. We'll look at a lot of examples to hammer this in. If you're confused, don't worry, you're not the only one. The equilibrium between liquid and vapor depends on the pressure. So some of the water evaporates at any temperature. If you increase the temperature, more of the water will evaporate. That's good for right now. The dual definition, vapor pressure is the same as the saturation pressure numerically. Vapor pressure, the liquid evaporates until its partial pressure is equal to the vapor pressure. Saturation pressure says if the total pressure drops below the saturation pressure, the liquid will boil. And they are the same number numerically. So if there's no other species in the vapor, then the partial pressure is the total pressure, and these two are the same. You can see that from this thought experiment. The speed of evaporation depends on the difference between the partial pressure and the vapor pressure. So basically the vapor pressure is the equilibrium partial pressure that gas species will have. It's not always in equilibrium, but if you wait long enough, it's going to approach it. So for example, water at 20 degrees has a vapor pressure of 2.34 kilopascals. How much water is required to saturate an initially dry room with a volume of 10 cubic meters? You can assume that the room is filled with dry air at 1 atmosphere. The way to do this is to use the ideal gas law to figure out how much water is required. So the water is going to evaporate until its partial pressure is equal to 2.34 kilopascals. That's the new information. The old information, which is from first year chemistry, is how much water does it take to build up to a pressure of 2.34 kilopascals in a 10 cubic meter room. So here's the calculation, and you end up with 9.61 moles, or 173 grams, or 173 milliliters of water. This means that an amount of water up to 173 milliliters left in an initially dry room with no ventilation at 20 degrees C will completely evaporate, but any more water won't. Now, what about if it wasn't filled with air? What if it was filled with nothing? What if it was vacuum? How much water would you need to completely evaporate into the room then? Well, it's actually the same. If there was more than 173 milliliters, then the first 173 would evaporate to bring the pressure of water, partial pressure is just the total pressure then, to the vapor pressure, 2.34 kilopascals, and then no more will be able to evaporate because we're in equilibrium. So it doesn't matter actually if the room is in vacuum or if it's filled with dry air. Now, let's look at the vapor or saturation pressure of water at various temperatures. As you increase the temperature, you probably can guess that the saturation pressure goes up. That's why water tends to start boiling if you put it to above 100 degrees C, but you don't normally see your glass of water vaporizing away before your eyes when you're holding it at 15 degrees C. So the one at 20 degrees C we saw already is 2.34 kilopascals, and then it goes up to 3 at 25, it goes down to 1.71 at 15. This is changing quite a lot. The low changing numbers on the right have to be balanced with what the scale is doing on the left, so it's not all the same difference as we go from one interval to the next. We've got a 50 degree temperature change here. So saturation pressure changes a lot with temperature. So here's some follow-ups. You leave your 400 milliliter glass of water in an initially dry room from the last question and wait a long time before returning. How much water is left in the glass? All right, well, if 173 milliliters evaporate, then there must be 227 milliliters left. When you return, you notice the room has two pipes, one carrying hot water and the other cold water. One of the pipes is damp, but the other's dry. Without feeling them, which one do you think is the hot pipe? Well, the one that's dry is going to be the hot pipe. And the reason is that the colder water pipe, maybe it's at 10 or 15, is going to have a lower saturation pressure. So the water that evaporated in the room is going to get, maybe it's evaporated to a partial pressure of 2.34. So you've got some pocket of air that has a partial pressure of water of 2.34 kilopascals. It gets close to that pipe, and now the temperature is lower because the pipe is cold. So the partial pressure there is only 1.23, and now that water vapor is above the saturation pressure, so it condenses. It deposits itself onto that pipe. If you think about this for a minute, then you can figure out why it is that your glasses fog up in the winter and when they fog up. So why does a sealed can of pop get all wet after you take it out of the fridge and put it on the counter for a while? Is it leaking? No, it's just colder than the air, colder than the surroundings. So the air that goes up to it probably had some water vapor in it, which was at a partial pressure above what the saturation pressure is for water at the cold temperature of the pop. Some other terms, the dew point, which is the temperature where the current water partial pressure will equal the saturation pressure. Water is not always completely saturating the air. The fraction that it's saturating the air is the relative humidity. So if you know that the humidity is 80%, that tells you that the current partial pressure of water is 80% of what water's saturation pressure would be for that temperature. So let's look at this. If it's 25 degrees and 80% humidity, that means it's 0.8 times 3.2. So 0.8 times 3 is 2.4. Maybe that's like 2.5, 2.56, I think. 2.5 kilopascals would be the partial pressure of water vapor. So if the partial pressure is 2.5, then it means if we were to drop to, say, 20 degrees somewhere, then it's above the saturation pressure, so water is going to start to condense. The dew point would be whatever temperature it is where water is going to start to do that. It depends on the air temperature and the humidity. Okay, if you're told the dew point in a power plant is 10 degrees C, what is the partial pressure of water? Okay, well, the saturation pressure at 10 degrees C is 1.23 kilopascals, which means the partial pressure is 1.23 kilopascals. Note that we didn't give the temperature in the power plant. You don't need to know the temperature to figure out what the partial pressure of water is if you know the dew point. So the dew point being 10 tells you that whatever the temperature is in the plant, 15, 20, 25, 30, the partial pressure of water is 1.23. If the temperature in the plant was 20 degrees and the partial pressure is 1.23, that means that the humidity is 1.23 over 2.34. So that's like, what is that, like 55%? If, on the other hand, the temperature in the plant is 30, so it's a pretty hot plant, then if the dew point is 10, the humidity must be 1.23 over 4.25, so it's only like 30% humidity. The dew point is really just telling you directly what the partial pressure of the water is. To say that the dew point is 10 tells you that the partial pressure is 1.23, and if you knew instead that the partial pressure was 1.23, you could go to this table and say, all right, well, what does that mean? If the temperature is above 15 or anywhere above 10, then that partial pressure is not enough to start condensing because it's the equilibrium would want more water to evaporate than there is. So none of it's going to condense. But if the temperature goes to 10 or below, then there's too much partial pressure of water. There's too much water evaporated, and it's going to start condensing. Less of it would be in the air in equilibrium. The lower we go, the more of a difference between the partial pressure and the current vapor pressure, and the faster it's going to start condensing. All right, one more example. If it's 30 degrees with 60% humidity, what is the dew point? All right, what you would do is go back up to this table. 30 degrees, 60% humidity means the partial pressure of water right now is 60% of what the saturation pressure would be. So 0.6 times 4 is 2.4, and then another 0.2 would be 2.5. So that means it's somewhere in here. So 30 degrees, 60% humidity means, if we've done our math correctly, then the dew point should be maybe around 22 degrees or 21.5. All right, so basically what we figured out here is that if you have some water vapor and it finds itself that's at a pressure which is above the saturation pressure, so if there's too much of it, like when the temperature gets lower, then what starts happening is it condenses. So if it is, it kind of becomes more liquid, more of it transforms into liquid. If the partial pressure of water is too high. On the other hand, if the partial pressure of water is too low, so we are at maybe 20 degrees, the partial pressure of water is 1.23, we've got some liquid present, then it's going to want to evaporate until it gets to 2.34. So I have a question for you. What do you think happens if you are inside a liquid system? So you put a bunch of water in some kind of a sealed container, and then you pull the container so that it increases volume, right? So you try to kind of pull the liquid apart, which is going to end up decreasing the pressure inside that liquid. What do you think happens? Well, at some point, the pressure inside the liquid is going to lower below the saturation pressure. So since liquids are pretty incompressible, if you actually pull apart the container, that's going to happen pretty quickly. It's going to stop being 1 atmosphere of pressure near the top and then like some hydrostatic increase near the bottom, and go quickly a lot lower than that. And you'll find that water will start to form pockets. This happens inside pump systems too, and it's called cavitation. If the pressure inside a fluid drops below the vapor pressure, so this happens at low pressure points like the suction end of a pump or the impeller blade tip, then the fluid can form vapor bubbles called cavitation bubbles. Now, somewhere else in the fluid, the pressure is probably higher, so the bubbles collapse again, and this can cause really intense pressure waves that can, over time, put damage into steel plates. So here's an aluminum sample showing some pretty extreme cavitation there. This is a thing to watch out for, since the lowest pressure in your system typically happens around pumps, especially pump blades, and those are one of the most fragile and expensive things in your pumping system. It's very important to pay attention to how much pressure you have feeding your pump to make sure that it never drops low enough that you can have cavitation happening. Cavitation is sometimes used to an advantage in engineering design. Here's a supercavitating torpedo, the Shikval. This is in service by the Russian Navy. Basically what it does is it generates cavitation around the torpedo as it's firing so that it gets to deal with mostly air drag rather than a much more potent fluid drag. Supposedly, it's able to go around 560 kilometers per hour underwater, which is pretty crazy.